Welcome, data scientists and enterprise architects. Today, we are mastering Snowflake Cortex fine-tuning. We will explore how to take industry-leading base LLMs and train them on your specialized enterprise data to achieve unparalleled accuracy. Let's dive in. Let's establish a foundational understanding of Cortex fine-tuning. As an enterprise architect, you know that off-the-shelf large language models are incredibly smart, but they lack deep knowledge of your company's specific jargon, tone, and niche domain workflows. Cortex fine-tuning is a fully managed service inside Snowflake that bridges this gap. Instead of training a massive multi-billion parameter model from scratch which costs millions of dollars, Cortex uses parameter-efficient fine-tuning, or PFT. This technique creates a lightweight customized adapter that sits on top of a base model like Llama 3 or Mistral. The greatest advantage here is security. Because this is entirely native to Snowflake, your proprietary training data never leaves your governance boundary. You simply call a SQL function or use the Snowsite UI, and Snowflake handles the complex distributed compute infrastructure required for model training. Look at this architectural flowchart. On the left, you provide your proprietary enterprise data, formatted as prompt and completion pairs. This data is securely fed into the Cortex fine-tuning engine alongside a state-of-the-art base LLM, such as Llama 3. The engine performs parameter-efficient training, meaning it only updates a small subset of weights, resulting in a customized model adapter. This adapter is then merged with the base model at inference time, giving you a highly specialized, secure enterprise AI that understands your specific business context perfectly. Why should you invest time in fine-tuning instead of just relying on prompt engineering or retrieval-augmented generation? The answer comes down to accuracy, latency, and cost. While RAG is excellent for retrieving facts, it struggles to teach a model a specific writing style, complex output formatting, or dense industry jargon. Fine-tuning solves this. Furthermore, fine-tuning allows you to achieve a phenomenon known as model distillation. You can take a small, lightning-fast model like an 8 billion parameter model, fine-tune it on your data, and watch it outperform a generic 70 billion parameter model on your specific task. This drastically reduces your inference latency and compute costs. Finally, because the fine-tuning happens directly where your data lives in Snowflake, you completely eliminate data egress charges, compliance headaches, and the risks of sending sensitive enterprise data to third-party AI APIs. This diagram contrasts the three main AI optimization strategies. Prompt engineering is your starting point, low cost, but low deep customization. RAG injects high context, but can increase latency because you are passing massive documents into the prompt every time. Fine-tuning, on the right, embeds the knowledge directly into the model's weights. This provides deep customization and low latency, leading to the highest return on investment for highly specific, repetitive enterprise tasks. Often, the best architecture combines both RAG and fine-tuning for ultimate performance. To implement Cortex fine-tuning, you follow a straightforward, four-step workflow. Step 1 is data preparation. You must format a Snowflake table or view so that it explicitly contains two columns, prompt and completion. The prompt is the input, and the completion is the exact perfect answer you expect the model to learn. Step 2 is initiation. You execute the fine-tune SQL command, or use the AI Studio UI, specifying your base model and pointing it at your training data. Step 3 is monitoring. Because training a neural network is a heavy computational task, it runs asynchronously in the background. You use the fine-tune describe function to check its progress. Finally, step 4 is inference. Once the job completes, your custom model is automatically registered in the Snowflake Model Registry. You can immediately start using it in your production pipelines by calling the standard cortex.complete function with your new model's name. Let's trace this workflow via a sequence diagram. The data engineer starts by formatting data in Snowflake tables. Next, they trigger the fine-tune create function against the Cortex engine. The engine immediately returns a job ID so the engineer isn't blocked. Using this ID, the engineer periodically polls the engine using the describe command to monitor progress. Behind the scenes, once training converges, Cortex securely saves the tuned weights into the Snowflake Model Registry. The engineer can then immediately query the model registry using the standard complete function to generate predictions at scale. Let's dive deep into the most critical phase, preparing your training data. In machine learning, your model is only as good as the data it learns from. Snowflake requires your input query to return exactly two columns named prompt and completion. If your source tables use different names, simply use SQL aliases. How much data do you need? A common misconception is that you need millions of rows. In reality, for PFD fine-tuning, you should start with just a few hundred highly curated, perfect examples. High-quality, diverse data always beats sheer quantity. You must also be mindful of context limits. Every model has a maximum token window, for example, 8,000 tokens for Llama 3.8b. Ensure your combined prompt and completion text fits well within this limit, or it will be truncated, ruining the training. Lastly, while optional, providing a separate validation dataset allows the system to test the model against unseen data during training, preventing overfitting. This class diagram illustrates the strict data contract required by the fine-tuning engine. Your training dataset and your optional validation dataset must both expose the exact prompt and completion string properties. Furthermore, both datasets must adhere to the structural constraints node shown at the bottom. The text must remain within the model's specific max tokens limit, which ranges from 8K to 32K, depending on the model, and you should aim for a minimum of roughly 100 high-quality rows to see meaningful behavioral changes in the LLM. Once your data is ready, executing the job is seamless. You use the Snowflake.Cortex.FineTune scalar function. The first argument is the action, which is create. Next, you define the name for your new custom model, followed by the base model you wish to tune, like Mistral 7v. Then, you pass the raw SQL queries as strings that will fetch your training and validation data. For advanced users, you can pass a final JSON options object to control hyperparameters. For instance, setting max epochs to 3 dictates how many times the algorithm will pass over your entire dataset. By default, Snowflake determines this automatically, but controlling epochs helps manage both compute costs and overfitting. Because these jobs are long-running, you aren't stuck waiting. You can execute fine-tune with the show argument to see all active jobs in your account, or cancel to immediately halt a job if you notice an error in your training data. Here we see the functional routing of the fine-tune command. The core function acts as a unified controller. By changing the first argument, you branch into different operational states. Create initiates the pipeline, requiring your model parameters and SQL queries, optionally accepting hyperparameters before commencing training. The other branches show, describe, and cancel act as your administrative lifecycle controls, allowing you to monitor active runs, check detailed loss metrics, or terminate jobs to save compute credits. A critical architectural decision is choosing your base model and securing the workflow. Snowflake provides access to top-tier open-weights models optimized for tuning, such as Meta's Llama 3.1 family and Mistral's 7v and Mixtral models. A senior best practice: don't automatically choose the massive 70 billion parameter model. Often, a 7v or 8b model fine-tuned on excellent data will achieve the exact same accuracy for a niche task, but at a fraction of the inference cost and latency. Security is also paramount. Snowflake enforces strict role-based access control. The role initiating the training must have usage privileges on the database holding the training data and create model privileges on the schema where the tuned model will be saved. Additionally, because this utilizes Snowflake's AI compute, an account admin must explicitly grant the Snowflake.Cortex user database role to the developer, ensuring AI spend is tightly governed. Let's review the security and selection matrix. On the left, the account admin delegates power by granting the Cortex user role to the data scientist. The data scientist must also possess standard Snowflake RBC rights, usage on the training database, and create model on the target schema. Once authorized, the scientist reaches the model selection gateway. They must weigh their use case, opting for the top path of 8B or 7B models for fast, cost-effective processing, or the bottom path of 70B models for highly complex, deeply nuanced cognitive tasks. Let's apply this to a highly valuable, real-world scenario: legal contract structuring. Imagine a legal firm that processes thousands of messy contracts. They need to extract specific liability clauses and output them into a strict JSON schema for their analytics dashboard. When they tried using generic LLMs, the models frequently hallucinated legal terms or returned broken JSON with conversational filler. The solution is Cortex fine-tuning. The engineering team takes 500 historical contracts. They map the raw contract text to the prompt column and the human-verified, perfectly formatted JSON to the completion column. They use this to fine-tune the highly efficient Mistral 7v model. The result: the fine-tuned model essentially unlearns conversational chat and becomes a dedicated extraction machine. It achieves near-perfect JSON adherence and runs at a fraction of the cost of a massive model, parsing millions of rows reliably via the AI complete function. This sequence diagram illustrates the streamlined production pipeline post-training. Raw contracts feed directly into our newly tuned Mistral 7B model as prompts. Because the model was trained specifically on our corporate JSON schema, it bypasses generic chatting. As noted, it applies its fine-tuned extraction patterns to instantly output a clean JSON object, like liability cap equals 50,000. This perfect structured data flows directly into our relational database, allowing downstream BI dashboards to parse and visualize enterprise risk cleanly and automatically. Finally, let's address enterprise observability and cost management. Fine-tuning bills you for the tokens processed during the training phase. Remember, after training, you are still billed for standard token consumption during inference. To audit your training spend, administrators should query the Cortex fine-tuning usage history view in the account usage schema. From a data science perspective, once training finishes, you must verify the model learned correctly. You can access the training results.csv artifact directly in the model registry to review the step-by-step training loss metrics. Lastly, a critical architectural note: fine-tuned models do not currently support cross-region inference. The inference compute must happen in the same region where the model object is stored, that you can use database replication to move the model. Master these concepts, and you will unlock incredible AI ROI. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final diagram illustrates the crucial observability and deployment loop. The training process immediately generates training tokens build, which you monitor via account usage views. Simultaneously, it generates the training results artifact. As a data scientist, you hit a decision gate. Did the training loss decrease appropriately? If no, you must go back and refine your training data. If yes, you deploy the model to production. Once deployed, the model generates ongoing value, tracking standard inference tokens billed locally within your secure region. Thank you for joining this masterclass, and please visit quicktechie.com.